Hi everyone, Miss Caulfield here. In today's video, we are going to be taking a look at radioactive decay and half-lives and how that relates to the concept of the atom. To start us off, it's important to know a little bit about the history of radioactivity and what radioactive activity is. So radioactivity can be defined as the spontaneous emission of radiation in the form of particles or high-energy photons that are resulting from nuclear reactions. This idea of a photon is a light particle. So in other words, radioactivity is the idea of particles or light particles being resulted from a nuclear reaction. The first people to use this term radioactivity were Marie and Pierre Curie, who we see here on the right-hand side of the slide. They were the first ones to study radioactivity and define what it is, and through their work with radioactivity, they were exposed to lots of radiation, which ultimately led to their deaths because of how harmful radiation can be to the body. After they had started to study radioactivity, a scientist that we are pretty familiar with at this point, Ernest Rutherford, continued their work and actually discovered that there are 3 different types of radioactive emissions. And so in this video, we are going to be looking at what those 3 types of radioactive emissions are. Before we take a look at what the 3 types of radioactive emissions are, let's look at why atoms go through these radioactive emissions. So all atoms want to be stable. That is the goal of an atom's nucleus. So all atoms want to have the highest stability they can. So when atoms are not stable, they are going to go through radioactive decay to try and increase their stability. We can tell if a nucleus is stable or not based on the neutron to proton ratio. Our light nuclei, or atoms that have an atomic number of 20 or below, want to have a proton to neutron ratio of 1 to 1. Our heavy nuclei, which are atoms that have an atomic number higher than 20, want to have a neutron to proton ratio of 1.5 to 1. So let's take a look at how we can determine the stability of an isotope. Remember, isotopes are atoms of the same element with different numbers of neutrons. Here we have 3 atoms of carbon. We've got carbon 12, carbon 13, and carbon 14. Remember, these numbers here, the 12, 13, and 14, refer to the mass number. So the mass number is equal to protons plus neutrons in an atom. And since we know we're looking at 3 atoms of carbon, we know that the atomic number, or the number of protons, has to be the same, and the atomic number of carbon is 6. So since carbon is a light nuclei, it has an atomic number of 20 or below, it wants to have that 1-to-1 ratio. Oh, that was a really bad color. Let's go ahead and erase that. It wants to have that 1-to-1 ratio of neutrons to protons. And so when we compare these 3 different isotopes, the most stable of the 3 isotopes is going to be the carbon 12. And the reason that it is the most stable is because that is where we see that 1-to-1 ratio of the protons to neutrons. All right, so when atoms aren't stable, they are going to go through radioactive decay to try and increase their stability. So what we're going to be looking at next are what are the 3 different types of radioactive emissions. The first type of decay that we're going to talk about is called alpha decay. Alpha decay is going to occur naturally with atoms that have 83 protons or more. In alpha decay, an alpha particle is going to be emitted, which we can see here on the left-hand side of the screen. This is what an alpha particle looks like. And an alpha particle actually corresponds or looks the same with a helium atom. So when you are writing an alpha decay nuclear equation or nuclear reaction, you could see it written with an alpha particle or a helium atom as one of the two products that is going to be formed. When we take a look at alpha decay, we see that both the protons and the neutrons are going to be reduced through alpha decay, because we see that the alpha particle is going to have a mass number of 4 and an atomic number of 2. So both the protons and the neutrons are going to be reduced through alpha decay. Let's go ahead and take a look at an example of an alpha decay problem. So here we are looking at polonium-210. Remember, this 210 here is the mass number of the isotope. So we're going to start by writing 210 with polonium. And when we look at our periodic table, we see that polonium has an atomic number of 84. So that is what we are going to start with on the left-hand side of our equation as our reactant. And we're going to draw an arrow to show that this atom is going through nuclear decay. We know, since it's going through alpha decay, that an helium atom, or an alpha particle, is going to be emitted. And now we have to try and figure out what our second atom that will be formed through this alpha decay would be. Well, to determine that, we're going to have to balance this equation. So looking at the mass number, we have to figure out what the mass number of this atom would be when we add 4 to it, it equals 210. So in other words, we're going to do 210 minus 4 to determine the mass number of our second atom. So we know the mass number of the second atom is going to be 206. And then we're going to do the same to figure out the atomic number. So we're going to do 84 minus 2 to figure out the atomic number of this second atom is going to be 82. Then we're going to go back to our periodic table and figure out which element has an atomic number of 82. And when we identify that, we realize that it is going to be lead. So this is how you would write the alpha decay of polonium-210. My tip is to always start with the alpha particle or the helium atom, and then use subtraction to figure out what your second atom would be. Our second type of decay is called beta decay. In beta decay, we think about this as a gain of an electron, and we'll talk about why we think about it as a gain of an electron in just a second. In the middle of your screen, you see two different particles like we saw for alpha decay. We have an alpha particle, which corresponds to a helium atom. Here on the left-hand side, we have a beta particle, and this beta particle is corresponding with the idea of an electron. So let's go ahead and start writing this beta decay of carbon-14. Again, remember, this 14 is the mass number. So we're going to start by writing the mass number with the element symbol. From our isotopes of carbon a few slides ago, we realized that the atomic number of carbon is 6. We're going to draw our arrow to show that this is decaying. Because it's going through a beta decay, we're going to go ahead and start by writing that electron or that beta particle, whichever you prefer. And then we have to figure out what our second atom is going to be. So just like we did for the last one, we're going to do 14 minus 0 to get 14 as the mass number for our second atom, and then we're going to do 6 minus negative 1. Remember, when you're subtracting a negative number, it's really like you are adding them instead, and so this is how we end up with getting 7 as our atomic number for the second element. And then we're going to go to our periodic table, figure out which element has an atomic number of 7, and we identify this as nitrogen. The reason we think about this as a gain of an electron, so remember, the atomic number is always equal to the number of protons in an atom. Well, in a neutral atom, remember, neutral atoms have no charge. We need to have the same number of protons as we do neutrons. So when that atomic number of protons is increasing, we also think about that as an increase in the number of electrons, because the electrons have to cancel out that extra positive charge. So the last type of radioactive emission that we're going to talk about is a process called gamma radiation. So in gamma radiation, Instead of the release of a particle, gamma radiation is simply put as the release of energy. So there is no change to the mass of the atom, but just a large amount of energy is released through this process of gamma radiation. Those gamma rays have no charge, and gamma decay often occurs with another type of decay. So gamma radiation is a type of radiation where it is just an emission of energy. In this image here in the middle, this is the Greek letter for gamma, so you could see this written to indicate that gamma radiation is occurring. So coupled with the idea that atoms are going to go through nuclear decay to increase their stability, we can actually determine how much decay occurs through this concept of half-lives. So the rate of decay is measured by the half-life of a radioisotope. Radioisotope is just an abbreviation for radioactive isotope. So the amount of time that it takes for 1/2 of that isotope's nuclei to decay is known as the half-life of that radioisotope. So let's take a look at this graph here. At the start of the graph, we have a ton of potassium nuclei, and as the graph progresses along the x-axis, so as time passes, we see that those numbers of potassium nuclei are decreasing, and that the number of argon and calcium nuclei are increasing because those potassium nuclei are decaying into different daughter isotopes. Well, the amount of time it takes for us to go from all of our potassium atoms, which is this first circle here at the top of the graph, to half of the potassium atoms, nuclei remaining, that is known as a half-life. So the half-life of potassium, according to this graph, would be 1.3 billion years, because that is the amount of time it takes to go from all of the potassium nuclei to half of the nuclei decaying. So not only is it important for us to be able to read and interpret a graph showing half-life, but we also want to practice our skills of being able to calculate how much of a substance remains based on that element's half-life. A really common example of where you would see this used in everyday life would be with radioactive dating of fossils and looking at the amount of different carbon isotopes within the fossil to determine how old the fossil is. So here we see we've got two different equations, and we're actually going to start by looking at this bottom equation. In this bottom equation, we see that n equals t over t 1/2. So n, which is the number of half-lives, is equal to the total time elapsed, or the total time that has passed, divided by the time it takes for one half-life. So we always want to start by making sure we know what this n value is, because the n value is going to be used in our calculation for half-life. Here we see that our original mass times 1/2 raised to the power of n will tell us how much of that element remains based on how many half-lives have passed. So let's take a look at our first practice problem for calculating half-life. Here we see that the time for the half-life of zinc-71 is 2.4 minutes. We have 100 grams of the zinc-71 at the beginning of our experiment, and we're asked how many grams would be left after 7.2 minutes have elapsed. So the first thing we want to look at is, do we know how many half-lives have occurred? The answer to that question is no. We're not told in the problem how many half-lives have passed, but we do have the information to calculate how many half-lives have passed. So we're going to start by calculating that n value. Remember, n is equal to the total time that has passed, so 7.2 minutes, divided by the time it takes for one half-life. And so we're going to go ahead and plug that into our calculator, and we see that the n value is equal to 3. There are no units with n, because the units of time are the same in the numerator and the denominator, so those would cancel out and we would be just left with the number 3. The next thing we want to do is go ahead and plug it into that formula. So our original mass times 1/2 raised to the power of n is equal to our final mass. Our original mass in the problem is 100 grams times 1/2 raised to the 3rd power, since we found that in our first step. And when we plug that into our calculators, we get an answer of 12.5 grams. Because remember, grams are the only unit that we're looking at in the problem, so they would be the only unit in our answer. What we haven't looked at yet are our significant figures and how many significant figures there should be in our answer. Half-life is a known value, and remember, known values cannot be used to determine significant figures, so the only measurement in the problem is going to be this measurement of mass. This mass measurement of 100.0 grams has 4 significant figures in it, and so my final answer should have the same number of sig figs. And so to fix our answer so that it has 4 significant figures, we're going to go ahead and add a 0 after that 5, so that we have the proper number of significant figures in our answer. All right, let's go ahead and take a look at a second practice problem for half-life. In this problem, we see that osmium has a half-life of 21.5 hours. We have a 10-gram sample at the beginning, and we're asked how much of that would have decayed after exactly 3 half-lives. So this problem does tell us our n value. It tells us that we will have gone through 3 half-lives with that 10-gram sample. So we don't have to solve for n because it's given to us in the problem. But let's go ahead and fill in the rest of that formula. Our original mass times 1/2 raised to the n is equal to our final mass. We see our original mass is 10.0 grams times 1/2 raised to the 3rd. And when we plug this into our calculator, we get that the answer is 1.25 grams. Now remember, this 1.25 grams is how much remains. How much of that osmium 182 remains? But the question is asking us how much would have decayed, or how much did we lose? So we have to take this problem one step further, and we're going to do our original mass minus what has been left over to figure out the amount that has decayed. And so when we take a look at our sig figs for this problem, since our mass here has, that was the wrong color, let's try that one more time. Since the mass given to us in the problem has 3 significant figures, we want to make sure that our, sorry guys, I'm having some issues with the highlighters. Since this has 3 significant figures, we want to make sure our final answer has 3 significant figures, which it does, so we don't have to do anything to our final answer. It is fine the way it's written. The last thing we want to make sure that you're familiar with regarding nuclear reactions and half-life in chemistry is the term nuclear fission versus nuclear fusion. These two words sound very similar, and so they are easily confused. Nuclear fission is taking an atom's nucleus and splitting it into 2 separate nuclei, whereas nuclear fusion is taking the nuclei of 2 separate atoms and bringing them together to form a new larger nuclei. So we just want to make sure that you are familiar with those 2 terms and the differences between those 2. At this point, we have learned all that we need to know for nuclear decay equations as well as half-life calculations. Great job.